Hello all, welcome to Brilliant Qatar YouTube classes. Today we are going to discuss some questions from physics chapter atoms. Okay, we know in the chapter the major topics are like we have to start with Rutherford atom model. We discussed the evolution of atom models in that chapter. We started with Rutherford atom model through his alpha particle scattering experiment. So we'll start with that particular concept, followed by there was some drawback for Rutherford atom model, right? We know, and then Bohr's atom model. He was trying to explain the drawbacks, or he was trying to overcome the drawbacks of Rutherford atom model, and he proposed his own Bohr atom model. And the major topics of this chapter is concentrating in that particular concept. We have three postulates of Bohr atom model. And the backbone of the chapter is completely that Bohr atom model. So in that we explained the three postulates as I told you. Then we'll get expression for radius of an orbit. We'll explain velocity of electron in an orbit and energy of energy levels. We know Bohr called that orbits as energy levels because each orbit possesses a definite amount of energy, so it is called energy levels. And followed by atomic spectra. And towards the end of the chapter, we applied Bohr atom model into hydrogen atom. So Bohr model of hydrogen atom is the last topic that we discussed in the chapter. So when we analyze this topic wise in the past papers, you can see most of the questions, 33%, is based on hydrogen spectrum and equally important the energy level concepts. And we are getting more number of questions from this part, like how to explain energy levels, how atomic spectrum is actually it is the arrangement of frequencies or the radiations when electron excite from one energy level to the other, right? So energy level and related atomic spectrum, this is the hot topic of the chapter as per the analysis, because most number of questions for the past papers is coming from those two topics. And we get questions randomly from Rutherford atom model, alpha particle scattering experiment, regarding that impact parameter, and also distance of closest approach. Some randomly we get questions, but mostly the repeated questions we can see from these two topics. So we are going to concentrate some questions from that particular topic, and I'll try to cover all the topics of course, but most number of questions will be definitely from these two topics. Okay, I hope we can go straight to the questions. Yeah, question number 1. Rutherford alpha particle scattering experiment shows the most of the alpha particle pass through almost unscattered, undeviated, while some are scattered through large angles. What information does it give about the structure of the atom? See, we get a conceptual question, right? Nothing to calculate here, just based on purely concepts. Rutherford atom model, is based on the result or the observation he made from the alpha particle experiment, right? From which he observed most of the alpha particle passed through the gold foil undeviated. What is the conclusion from that observation is the question. Okay, look at the options. Option A says atom is hollow. Right, we know before Rutherford atom model we had J.J. Thomson's atom model, which says atom is a completely filled sphere. There is no empty space inside. It is like negative, positively charged sphere filled with negative charges. We know the J.J. Thomson's atom model. So that concept is demolished by Rutherford atom model, and you can see atom is hollow. That is the first option given. Second option, most of the mass of the atom is concentrated in the nucleus. Yes, Rutherford put forward that particular concept, right? Nucleus, central core of an atom. And look at the third option, nucleus is positively charged. Most of the mass and also all positive charges are concentrated at the center. That is called the nucleus. And option D, all of this. Yes, some of you already answered the question. Yes, okay. Option D is the correct answer. All of these observations, you can conclude all these three statements can be the correct conclusion of the first observation. Okay, right. Let us proceed to the next one. Again, based on Rutherford alpha particle experiment, question number 2. Rutherford alpha particle scattering experiment, what will be the correct angle for alpha scattering for an impact parameter B equals to 0? We know impact parameter is denoted by B, small b, right? Impact parameter is 0 here. then what will be angle of scattering is the question. If you want to answer this question, yes, Faris, yeah, I'm getting response. Yes, Hadia, yeah, correct, exactly, true, yes. So we know what is an impact parameter. When you have a nucleus, in that experiment we have gold nucleus, impact parameter is the distance, perpendicular distance between alpha particle, direction of alpha particle. If the alpha particle is going along this direction, it will be deviated like this, correct? And then you have to imagine a straight line passing through the center of mass of the nucleus. Perpendicular distance between these two lines is called the impact parameter. Sorry, we denote it by B, impact parameter. So you can see if impact parameter is 0, that particular alpha particle will pass, along this line. It is going to have a head-on collision, right? If impact parameter is 0, alpha particle is about to collide. The nucleus of the gold foil, that gold atom, head-on collision will be there. Because of that, the alpha particle is supposed to bounce back. Yes, Dhruvil. Yes, Angeline. Yes, exactly. So option D, it should be 180 degree, right? If impact parameter is 0, we'll get head-on collision. Like there will be 180 degree angle of scattering. And we observed most of them passed undeviated. For them, B is large, right? If B is large, theta is equal to 0. Theta is the angle of scattering that we know. This was the angle theta. If B is very large, they will deflected very less, so theta will be 0. If B is small, then they will deviate with larger angles, right? And if B is equal to 0, like in this question, it is a head-on collision, theta is going to be 180 degree. Yes, so we solved question number 2. Then third one, question number 3 is also a conceptual one. We have, according to Bohr's theory, the radius of electron in an orbit described by the principal quantum number n and the atomic number z is proportional to. Yes, we are coming to the Bohr atom model now. Bohr atom model, we had 3 important postulates followed by 3 equations, one for radius of the orbit and velocity of electron in an orbit and energy possessed by an electron, or which was called energy of the orbit or energy of the energy level. These 3 equations are really important, right? And their relation between principal quantum number n and these quantities. We get repeating conceptual questions from this part. Yes. Okay, and what was the expression for R? Radius of the orbit. It was epsilon 0 n square h square divided by pi m e square z. Right? This was the equation. Where epsilon 0 is the constant we know, permittivity of free space, h is the Planck's constant, pi is the numerical constant, m mass of electron another constant, e is what? Charge of electron, exactly. Yes, Hadia. Z is the atomic number, right? So we can say R is inversely proportional to, for a given atom, Z is going to be a constant, so we can say R is proportional to n square by Z, right? From this, if you consider Z is constant only for a given atom, if you change the atom, Z also is a variable, so n square by Z. So we have an option here, option D, right? D is the correct answer. Yes, and from this equation we concluded, we have taken that relation R is proportional to n square, right? This was the equation we got finally. So relationship between radius of the orbit and principal quantum number, R proportional to n square. This relation will help you to solve all these kind of questions, and we have some samples followed by this. Okay. Yes, so many of you answering it properly. Let's move on to the next question. Question number 4. Yes. The radius of innermost electron orbit of a hydrogen atom is 5.3 into 10 raised to minus 11 meters. Radius of the innermost orbit. Innermost orbit, the hint is n is equal to 1, right? Innermost orbit, n is equal to 1. Yes. What is the radius of the orbit in the second excited state? Be very careful, second excited state. N is not equal to 2 here. That's a very common mistake we commit in this question. N is not equal to 2, N is equal to 3, because we are talking about second excited state. right? We know after the ground state, the next possible, n is equal to 1, right? In hydrogen atom, n is equal to 1 is the ground state. Any higher energy levels are called excited level. So n is equal to 2 is a first excited state, n is equal to 3 is a second excited state, and so on. So here we are talking about second excited state, and we can say n is equal to, see, n is equal to 3 is to be considered. Second excited is going to be n is equal to 3. So we, as I told you in the previous question, r is proportional to n square. R is proportional to n square, that we know. So for the first orbit, when n is equal to 1, r1 is proportional to n square. That is going to be 1 square. That is 1. For the third orbit, which is the second excited state, for the third orbit, n is equal to 3, second excited state, r3 should be proportional to n square. That is, this time n is equal to 3. So we will get 3 square, which is going to be 9. So r1 by r2 you can simply calculate. r1 by r2 is going to be 1 by 9. So what will be r2? R2, right? That is like R3, actually not 2. R3 is a second excited level. R3 is equal to 9 times R1. You are given the value of R1 in the question, radius of the first orbit, right? You have to just multiply with 9. So R3 is going to be 9 into 0.53 or 5.3 into 10 raised to minus 11 meters. And we will get option A, 4.77 into 10 raised to minus 10 as the answer for this question. Yes, exactly. Yes, Azim. Yeah, r is proportional to n square. That is what I told you before. Right? R is proportional to n square is the result we obtained from the previous question. Right? We concluded like this, that we just used here in the question number 4. Yeah, hope I can continue. Fine. So we'll go on to the next question, question number 5. Again, a question related to the radius. Ratio of the radii of orbits corresponding to the first excited and ground state in the hydrogen atom. I told you they are trying to be tricky, like first excited. We should be very careful. Don't be sticking to this. It is not the first energy level. First excited. First excited, we know. First excited orbit is n is equal to 2. N is equal to 2. Because n is equal to 1 is called the ground state. Any higher energy level, n is equal to 2, n is equal to 3, and so on. They are called higher energy levels, excited energy levels. So the first excited is n is equal to 2. Right, and the ground state in hydrogen atom. You are asked to just find the ratio of the radii. Again, a simple question. We can find out radius of the first one. R1 is proportional to 1 square. We still use the same relation. R proportional to n square. Correct? R proportional to n square. Yes. Yes, Albert, Angeline, Azim. Correct answer. Fine. So we got the ratio. R1 is 1 square. R2 is proportional to 2 square. So if you just take the ratio R1 by R2, we get 1 by 4. Right? So first excited to second excited. So we have two options. Remember, don't be confused. 1:4 is given, 4:1 is given. The ratio you are asked to find R2 by R1, second excited to the ground state. So R2 by R1 is going to be 4 by 1. Don't go for 1:4. Answer is 4:1. Option C. Yes. Okay. So these are some questions from radius. So remember, most of the questions from this part, we have to use the relation R proportional to n square. Right? Because we never get questions based on that long equation that I told you. Radius is equal to epsilon 0 n square h square, this long equation, you know. Right? We get questions always like these kind of relations. So R proportional to n square or R proportional to n square by z, this relation also. Remember both the relations. That is enough to solve questions from this radius related questions. Okay, fine. So that was question number 5. Then sixth one. Question number 6 is about like the second postulate of Bohr atom model. Bohr atom model, we know, I told you about the 3 postulates. Postulate number 1 was about revolution of electron in non-radiating orbits. Yes. Yeah, yes Azim, yes Albert, Hadia, yes Reshma, exactly. So we are all answering it properly because it's a very simple question, right? We have the second postulate, which is regarding the angular momentum. Angular momentum is mvr for a given orbit will be integral multiple of h by 2 pi. mvr is equal to nh by 2 pi is the relation. So you are asked to compare angular momentum of, you are asked to calculate angular momentum of electron in the ground state of hydrogen atom. Ground state of hydrogen atom, n is equal to 1, right? N is equal to 1. So if n is equal to 1, your answer will be just h by 2 pi. Angular momentum is mvr. If you have to just remember the second postulate, its mathematical expression, you can easily solve this. mvr is equal to nh by 2 pi. So h by 2 pi, option C is the correct answer for question number 6. Okay, right. Then moving on to the next one, 7. Yeah, yes, keep answering. Okay, the ratio of angular momentum of an electron in first orbit to that in the second orbit. Yes, whenever we are talking about orbit, I'll tell you once again, repeatedly I'm saying the same, like check whether it is the orbit or excited state. Okay, so in this question it is first orbit and to the second orbit, nothing to be confused. They're talking about orbits only, not excited states. Yeah, I'm looking for the answers. Yes, yes Abel, Shalom, yes Hafiz, hello Hafiz, yes Nidin, yes Albert, yeah Hadia, Kirtiraj, yes, hi. Yes, yeah, check Hadia. Oh, it's A only. Yes, correct only. So we got that ratio mvr is equal to nh by 2 pi. nh by 2 pi. You are asked to find the ratio between first and second orbit. If it is first orbit, n is equal to 1. For second orbit, n is equal to 2. So the ratio is basically going to be nh by 2 pi. For the first one, it will be h by 2 pi. For second one, it is going to be 2h by 2 pi. So if you take the ratio, h by 2 pi is going to be cancelled. 1 by 2 will be the ratio, right? h and 2 will be cancelling, and we get only 1 by 2 in the, right, in the ratio. So option A is the correct answer for question number 7. Okay, so those two questions were related to second postulate of Bohr atom model. Right, angular momentum of an electron revolving in an orbit is always equal to integral multiple of h by 2 pi. Okay, moving on to the question number 8. Yeah, we are coming to the energy part. I told you about in Bohr atom model, the 3 postulates of Bohr atom model. First one we discussed already. Second one was related to the angular momentum, right? And third one is about energy levels, we know. Yeah, and we are coming to that energy part, and this was the most important, energy levels and that energy transition or the atomic spectrum. When I showed you that topic wise weightage, we are coming to that important session now. Okay, see, we know energy expression, energy of electron in a given orbit is going to be z square m e raised to 4 divided by 8 epsilon 0 square n square h square with a minus sign. Total energy of an electron in an orbit is always negative. Bound system, right? We know what does it mean. Electrons are revolving around the nucleus, making use of electrostatic attraction between nucleus and the electron. That was the first postulate of Bohr atom model. Right, he says the necessary centripetal force required for this circular motion is provided by electrostatic force between nucleus and electron. Nucleus has positive charge, electron is negative charge, so there will be an attraction. Okay, so it is a bound system, that is why negative. This is the total energy of an electron in a given orbit, and you can see most of them are constants, right? And we got simplified form of this. It is like minus z square by n square. When you simplify all those constants together, like mass of electron, charge of electron, epsilon 0 we know, permittivity, like h Planck's constant, we got 13.6, but the unit is in electron volt, right? So this much energy will be possessed by an electron, or that is the energy of any energy level. N is the number of that particular energy level. which is called principal quantum number. Yes. Okay. This was the total energy, and we know kinetic energy equation. Kinetic energy, total energy of an electron in a given orbit, or total energy of an energy level, is actually sum of kinetic and potential energy of an electron revolving in it. So if this is the total energy, kinetic energy equation, we know it is plus z square m e raised to 4, correct, divided by 8 epsilon 0 square n square h square. The only difference is total energy is negative, then kinetic energy will be positive. 1:-1 ratio, right? Kinetic energy and total energy is the ratio 1:-1. Okay, and potential energy of the electron. So I will use PE, potential energy of the electron, or potential energy of the electron in that particular energy level. It was minus z square m e raised to 4 divided by 4 epsilon 0 square n square h square. Yes, I am just running through that equations because in the coming questions we may be using them. Okay, just to get a review of the things. So kinetic energy, potential energy, and total energy, we have these equations, and we know that relation kinetic energy is to potential energy is to total energy of that energy level is in the ratio I told you already 1:. If your kinetic energy is 1, then potential energy will be minus 2 times of that, and your total energy will be minus 1 times of the kinetic energy. We have this ratio, and this ratio helps us a lot to find like any energy, like either kinetic energy, potential energy, or total energy, if you are given any one of the energy form of that particular energy level, you know, this ratio. Okay, now, so these are the things you have to remember. Equations we have from energy part, kinetic energy, potential energy, and total energy part. Now look at the question. The ratio of energies of hydrogen atom. Yes, we are going specifically for hydrogen atom. The advantage of that, your Z value will be 1. We noted that Z is equal to 1 in its first to second excited state. Talking about excited state, this is the common, like, you know, I have to repeat this again and again because in almost all the questions they either use excited state or energy level, right, frequently. So this time it is excited state, first excited to second excited state. As I told you before, first excited is yes Siddharth, yeah, exactly. First excited state is going to be n is equal to 2, second excited is n is equal to 3. So now you can easily find out using this relation. So since it is hydrogen atom, this Z also will be 1, right? So we can just simplify that. Is like energy En is equal to minus 13.6 divided by n square. Yes, because Z is equal to 1 here. That Z is also good. Hydrogen atom. Okay, so n is equal to 2. That is a first excited. N is equal to 3 is a second excited. We have to just substitute them. So first one is minus 13.6 divided by 4. And the second one is going to be minus 13.6 divided by 9 n square. So 2 square and 9 square, will mean 3 square will be coming in that respective equations. So just take the ratio. E1 by E2. What will be the result? Minus 13.6 will be gets cancelled. 1 by 4 divided by 1 by 9. So we get 9 divided by 4. Right? That was one of our options. I hope. So we'll go back. Yeah, option C. That was 9 by 4. Right? Yes. Okay. Question number 9. Another question from the energy part. Let's go through that. How does the energy difference between two consecutive energy levels vary on the quantum number n increases? Simply means what happens to the difference between adjacent energy levels when you go from one orbit to the other, when you're coming towards the higher energy level, starting from the lower energy level or the ground state energy. If you come into the first excited, second excited, third excited, and so on. Yes, and that energy difference between the energy levels, that is a question. Okay, so we know when you represent energy levels, energy level representation, if this is the ground state, this is the first excited, second excited, third excited, and so on. When we draw these energy levels, we reduces the difference, relative distance between the adjacent energy levels is decreased, right? Because we know the energy of these energy levels, delta E1, the first ground state energy is going to be minus 13.6 divided by n square into z square, whatever may be this atom, whether it is hydrogen or anything. So the general equation we are going for, minus 13.6 by n square into z square. The next one will be minus 13.6 divided by, that is 1 square, here it is 2 square into z square, and the next one will be minus 13.6 divided by 3 square into z square, and keep on going. And for hydrogen atom, we have those values, right? For if it is hydrogen atom, if z is equal to 1, right, we can say minus 13.6 electron volt was the energy level of the ground state, because n will be 1. When n is equal to 2, minus 13.6 divided by 4, which is going to be minus 3.4, and 13.6 by 9 minus 1.51, then minus 16, 13.6 divided by 16 is going to be 0.85, and so on. I told you we can remember these values for further references to solve these MCQ questions very easily. At least the first 4 energy levels of hydrogen atom, specifically for hydrogen atom when Z is equal to 1. Correct? Yes. And you can check, delta E1, energy difference between the first 2 is going to be 10.2 electron volt, right? 10.2 electron volt. Distance between the first 2 energy levels. And for the next 2, second and third, it is minus 1.51 minus 3.14. It is smaller than 10.2, and that difference is decreasing. That was our question. When you go to the higher energy level, difference in energy between energy levels will decrease. Yes, most of you answered it decreases. B is the correct answer. Yes, Dhruvil. Are you in a doubt? It's B only. B is the correct answer, right? But remember, one more point you have to remember related to this question. We are talking about energy levels here, right? First energy level, first excited, second excited, and so on. But when you talk about radius, when you represent the orbit in terms of its radius, see, this is the nucleus. The first orbit will be of like somewhat like this. How can you draw the second orbit? Second orbit should have a greater separation, greater separation. Third orbit should be even more, increasing the separation between the orbits. It's because when you go for the radius is proportional to n square. Do you remember? That was the first topic we started with, radius relation. R is proportional to n square. So when you represent orbits in terms of their radius, you have to keep that distance, separation between the adjacent orbits, that should be increasing. Whereas when you come to the energy level, that difference is decreasing. Therefore, they should be coming closer and closer when you go to the higher energy levels. Okay, so be careful whether you're talking about energy levels or orbit. This question was about energy. That is why option B is correct. When you come to the radius, separation between adjacent radius like orbits will be increasing when you come to the higher energy levels or higher orbits. Okay. Yeah, wavelength, we are coming to that part here. When we come to the energy transition, we have some questions related to that. We'll explain. Okay. And if you have confusions there, just let me explain at that time. Okay. Question number 10. The ground state energy of hydrogen atom is minus 13.6. What are the kinetic and potential energy of the electrons in this state? I want answers in 2 seconds, because we already explained the ratio between kinetic, potential, and total energy of an energy level, right? So tell me fast. Yes, Kirtiraj, Reshma. Yeah, so many messages I'm getting. So I'm sorry if I can't read all of them. Hadia, Azim, yes, Angeline, Khalid. Nitin, can you check your option? Shalam, you also? Yeah. Okay. So here we are given the total energy. Total energy is minus 13.6. Exactly. Total energy is minus 13.6. We know total energy is to kinetic energy is to potential energy is to total energy is in the ratio 1 is to minus 2 is to minus 1. So if your total energy is minus 13.6, what should be your kinetic energy? Kinetic energy will be just positive of that, right? That is the ratio 1 is to minus 1. Total energy and kinetic energy are in the ratio 1 is to minus 1. So your total energy is minus 13.6, correct? So your kinetic energy should be just positive of that. Check the options. Kinetic energy. We get kinetic energy minus 13.6 here, but that is not the correct answer because it should not be negative, right? Total energy is minus 13.6. So which option is correct? Yes, almost all of you except 1 or 2 just got it wrong. Option D, kinetic energy should be minus 13.6 electron volt. And what about potential energy? Potential energy should be minus only. Total energy and potential energy will always be in the same sign, minus, when kinetic energy is positive, right? Okay, and it will be 2 times the total energy or 2 times the kinetic energy. Kinetic energy or the total energy was 13.6. Twice of that will be the potential energy always. Kinetic energy, total energy, equal by magnitude, opposite by signs, like kinetic positive, total energy negative. Potential is, it has the same sign as that of the total energy, but twice of that. Yeah, that was easy, right? Yeah, since we knew this particular ratio, this question is quite easy. Option D is the correct answer. Question number 10. Okay, let's move on. Yes, those who asked me about the wavelengths, we are coming to it. Okay, the adjoining figure indicates the energy levels of a certain atom when the system moves from 2E to E level. A photon of wavelength lambda is emitted. So they are talking about one transition from 2E to E. As you can see, this is the transition they are talking about. At that time, there was an emission of wavelength of lambda. Now, wavelength of the photon produced during its transition from 4E by 3. You can see one of the energy level in the diagram. It has an energy 4E by 3. Yes, and that transition has been shown here, 4E to E. What will be the wavelength emission? We know whenever excited electrons coming back to their initial energy level, they will emit radiation, right? They emit radiation. Yes, that radiation has a wavelength or frequency proportional to the energy, like energy difference between initial and final orbits. So when the electron shifted or transferred from 2E to E, wavelength emitted was lambda. The question is, what will be the wavelength of the electron, wavelength of the photon when it is transmitted from 4E by 3 to E, lambda dash or something? What will be this value is the question. As far as, yeah, let us see. I think you got it wrong somewhere. Just check the calculation. Let's see. Electron is coming from 2E to E first. I'll go for that transition so that I can relate lambda dash and lambda finally. Okay, in the first transition, we know energy emitted when electrons transferred from one orbit or one energy level to the other, energy released during that process is equal to difference in energy, right? E final minus E initial. Correct? That is a difference in, that's energy emitted during the particular transfer. So we can say delta E. That delta E can be represented as H nu. Why H nu? This energy will be released in the form of radiations of definite frequency. Radiations of definite frequency, they will have a definite wavelength also. Energy of any radiation can be taken as H nu. And this time, question is not about the frequency, it is about wavelength. Therefore, we have to take this equation in terms of wavelength, which is hc by lambda, because we have a relation c is equal to nu lambda, from which we can say nu is equal to C by lambda, this relation that helps us to represent energy in terms of wavelength. So this is the equation I am going to use to solve this particular question. Energy released during this transition, E is equal to, or delta E is equal to hc by lambda. Okay, and as for the first transition, it is coming from 2E to E, so I will take that one as transition from 2E to E will give you a particular wavelength lambda, equation number 1. See, this is our delta E, correct? Delta E. For the first transition, delta E is 2E minus E. Energy levels are given, energy values are given, 2E minus E is equal to hc by lambda, equation number 1. Now, check the second one. The second transition is 4E by 3 to E. So, that there also we will form an equation. So, right now we got 2E minus E is equal to hc by lambda, equation number 1. For the second transition, what was the energy given? 4E by 3 and E. So, the energy difference will be 4E by 3 minus E will be hc divided by lambda dash. Yes, so we can just simplify this. 4E minus 3E, it is going to be just E divided by 3 is equal to hc divided by lambda dash. Why lambda dash? In the second transition, wavelength will be different from the first because energy difference is different, right? The energy difference is not the same. Equation number 2. Yeah, now you have to just take the ratio. Yes, most of you solved already. So we will get 2E minus E, that is going to be just E is equal to hc by lambda. So if I take the ratio of equation number 1 to 2, I'll get E divided by E by 3 is equal to hc by lambda divided by hc by lambda dash. This is going to be 1 by 3, correct? E gets cancelled and hc gets cancelled. I'll get 1 by lambda divided by 1 by lambda dash. Going to the next, so 1 by 3 is going to be 3. 1 by lambda dash is going to be lambda dash by lambda. Yes, you have to find lambda dash in terms of lambda. So we got it, the answer, lambda dash is equal to 3 lambda, correct? So the new wavelength will be 3 times, yes Dhruvil, exactly Hafiz. So lambda dash is equal to 3 lambda is your answer. That was option D, yes, the last option, right? 3 lambda. So that transition, you have to go for the magnitude of the energy difference that is equated to hc by lambda, right? Or h nu, depends on the question. If you're asked to calculate the frequency, stick into that h nu equation. If it is wavelength, go for hc by lambda equation. Okay, fine. Question number 12. You can see another question from the same concept based on the transition. Energy levels of an atom are as shown below. Which of them will result in the transition of a photon of wavelength 275 nanometer? Yes, look at the diagram given. You are given like 1, 2, 3, 4 energy levels. And their value of energy is given on the other side. First ground state energy is minus 10 electron volt, or the first energy level. Second energy level is minus 4.5. Third one is minus 2, and the last one is 0 electron volt. Okay, so energy of different levels are given. And transitions A is from 4 to 3, B is from 4 to 2, C is from 3 to 2, and D is from 3 to 1. This is the given information in the question. You are asked to find one of these transitions, A, B, C, or D, gives a radiation, emission of radiation, in which wavelength of that radiation is 275 nanometer. See, all the transition will emit radiation. It is coming from higher energy level to lower energy level. So there will be emission of radiation. And each radiation will have different wavelength because, their energy levels are different. Okay, let's see. I'm getting different options. Okay, let's find it out. Now, what will we do? We have an information here in the question. Emitted radiation has a wavelength 275 nanometers. Okay, 275 nanometers. But see here, there is no lambda term given. We have only energy differences given in the question. So what we can do, the best way of doing is like, we can find out what will be energy of this radiation, correct? If you can calculate what will be energy of a radiation which has a wavelength lambda, that energy you can cross check for all these transitions. Okay, what will be the energy emitted in the state, in the transition A? Energy emitted in the transition A is 0, minus 2, right? Fine, like this is the energy difference. It is going to be 2 electron volt. Energy emitted in the transition B is going to be 0 minus 4.5. It is going to be 4.5. B will have a transition 4.5 electron volt energy release. Transition C has 2 minus 4.5. Difference between the two is going to be 2.5 electron volt in transition C. Now for transition D, look at this, minus 2 minus 10, you will get 8 electron volt emission in transition D. So one of these energy is equivalent to this wavelength. You are asked to just find out which transition having this wavelength, you know, which a radiation emitted has this particular wavelength. So as I told you, we will find out what is the energy of this radiation, then we will cross check the options. That's the best way of doing it. How will you find energy of a radiation? If you know its frequency, it is h nu, but frequency is not given, it is wavelength, so hc by lambda, right? hc by lambda. Yes, Kirtiraj. Yeah, okay, be careful when you calculate. E is equal to hc by lambda. We are going to stick into this because we have only lambda. Okay, so let's see. E is equal to hc by lambda. We have given lambda is equal to 275 nanometers. Okay, hope you remember how can we calculate energy in electron volt from this equation, right? Yes, hc by lambda, if you go for h is equal to 6.626 into 10 raised to minus 34 is the Planck's constant. C is 3 into 10 raised to 8, right? Divided by lambda is 275 into 10 raised to minus 9, because we have to use all values in SI unit. H is given in SI unit, C is given in SI unit. So you have to convert lambda into SI unit meters, and you will end up with a value in joules, because SI unit of energy is also joules, right? So when you get energy in joule, you have to convert that back into electron volt to compare these energies. Otherwise you cannot identify which transition is the answer for this question. Okay, so instead of doing all these, we have a shortcut. I hope you remember that. E is equal to h c by lambda can be 12375 divided by wavelength taken in angstrom. Remember, angstrom is the unit. You have to take, you know, wavelength in angstrom. Then energy will be automatically obtained in electron volt. So energy obtained in electron volt, if you use this equation, right, provided your lambda should be in angstrom. So this will be the easiest calculation then, instead of going for all these and converting. And we know this, yes. So energy we are going to calculate using this equation. E is equal to hc by lambda. Remember to take lambda in angstrom. That is the point where we commit mistake in this when you use this shortcut. Okay, lambda should be in angstrom. But your given value of lambda is in nanometer. We know 275 nanometer is going to be 2750 angstrom. Converting nanometer into angstrom, just multiply with 10, because 1 angstrom is equal to what? 1 angstrom is equal to 10 raised to minus 10 meters, and 1 nanometer is equal to 10 raised to minus 9 meters. Yes, so just multiply with 10 to convert nanometer to angstrom. Then just substitute 12375 divided by wavelength in angstrom 2750. That will be your expected energy in electron volt, and that energy will help you to identify the transition easily. Yes, Kirtiraj. Okay, yes, Reshma. Yes, Hafiz. Exactly. So this was 4.5, right? When you simplify this, you will get 4.5 electron volt. Yeah, exactly, 4.5 electron volt. Okay, so then 4.5 electron volt, we already identified the transition energies. 4.5 electron volt was for the transition B, right? So when the electron transfers from the fourth energy level given to the second energy level, it emits an energy of 4.5 electron volt. If so, that radiation will have a wavelength 275 nanometer. So the transition B is the correct answer. Okay, yeah, it's a good question. We connected all the concepts together, right? Energy of the radiation emitted, transition of electron, how to find out energy release, wavelength frequency relation. Yeah, okay, fine. Question number 13. If the electron in hydrogen atom finished? Okay, fine, thank you. Then if the electron in hydrogen atom is excited to n is equal to 5, the number of different frequencies of radiation which may be emitted as. We know electrons can excite from its ground state into any other energy level. Hydrogen atom, we have only n is equal to 1 is a ground state. It can go to higher excited energy levels, and whenever it go to higher energy level, it can come back. It is coming back to the initial level, right? By emitting radiations, by emitting energy, we know. So in this case, electron is excited to n is equal to 5. N is equal to 5. How many transitions or how many frequencies of radiation can be possible? Like we know, if the electron de-excite or it comes back from one orbit to the other or one energy level to the other, it emit one radiation. When it comes from the same to the other one, right, you know, it emits another radiation. So how many radiations possible? 2 radiations possible here, because there are 2 transitions happening. Okay, so actually number of radiations you have to calculate, number of frequency of radiations is to be calculated. That is exactly equal to number of transitions possible. Correct? So basically, what is the number of transitions? Number of transitions possible when electron is excited to n is equal to 5. So if you are going to count it, from n is equal to 5, it can come back to n is equal to 1, or n is equal to 2, n is equal to 3, or n is equal to 4. Correct? Yes. An electron coming to n is equal to 4 can go back to the lower energy levels. So there are so many transitions possible. Correct? And we have an expression for that. Number of transitions is to be calculated. If you are given the energy level to which the electron is excited, from there, the possible number of transitions to the lower energy levels, n is equal to n into n minus 2 divided by, n into n minus 1 divided by 2. That is the equation, where n is the excited energy level. And in this question, it is given n is equal to 5. Right? N is excited, like n is equal to 5 is given in the question. So number of transitions possible in this is going to be 5 into 5 minus 1 divided by 2. That is 5 into 4, which is 20. 20 divided by 2 is going to be, yes, half is 10. 10 is option B, exactly. Right? So these many transitions are possible for an electron which is excited to n is equal to 5. Okay, so remember the equation. Number of transitions is going to be n into n minus 1 into divided by 2. N into n minus 1 divided by 2. Yes. Okay, see, actually what happens there, when an electron is excited from n is equal to 1 to n is equal to 5, 1, 2, 3, 4 and 5, right? Electrons are coming back. From here, it can go straight to n is equal to 1, right? Or it can go it can go to this, right? And it can go to the second orbit, possible to third orbit, possible to the fourth orbit, and even coming back to the initial orbit. An electron coming here can further come back to first, second and third, even here, right? So if you count all the possible transitions like this, you will get the number of possible transitions, but it is difficult, especially if we will come to the higher energy levels. If n is large, then it is difficult. There, this equation will help you to find out the number of transitions. Okay, right, moving on to the next question. Yes, yeah, that was 10 only. Now, if 13.6 electron volt energy is required to ionize the hydrogen atom, then energy required to remove an electron from the first excited state is. Here, hydrogen atom is going to be ionized. What do you mean by ionizing hydrogen atom? In hydrogen atom, we have one electron and we have to remove this electron, release that electron to ionize the hydrogen atom. How much energy is required for that? It is given that 13.6 electron volt. What do you mean by removing an electron from the orbit? We have to supply an energy to this particular electron so that it is free from the attractional force of the nucleus. So if it has minus 13.6 electron volt, we have to supply that plus 13.6 electron volt so that energy reduces to 0. It will be released from the atom. Okay, that is what actually happens. So it is given that 13.6 electron volt is the energy required to ionize the hydrogen atom. So first energy level, E1, has an energy minus 13.6 electron volt, right? That is a hint. Then what will be energy in the second orbit, second energy level? We know from the equation minus 13.6 divided by n square, right? Electron volt. So it is going to be minus 13.6 divided by 2 square, which is 4, and I told you to remember those 4 values, right? First one was minus 13.6, second one 3.4, minus 3.4, then minus 1.51, then minus 0.85, right? Those values will help you to find out easily. Here we are comparing, we have to find out the energy in the first excited state. First excited state is nothing but n is equal to 2, right? N is equal to 2. We know in the second orbit of hydrogen atom, since we remember that value, E2 is minus 3.14 electron volt. If you want to remove that electron, how much energy is to be supplied? We have to make the energy to 0. Before, minus 13.6 electron volt is converted to 0, like it's by adding plus 13.6 energy into it. Here minus 3.0 volt energy is the energy of that electron. So we have to supply same amount of energy but plus. Option C is the correct answer for this. Okay, so that is why every time when you get first excited or second excited of hydrogen atoms, don't calculate always minus 13.6 by 4, 13.6 by 16 or something like that. Instead, remember those values. Okay, at least the first 4 energy levels of hydrogen atom you can easily remember, and you can easily solve these kind of questions without wasting your time. Okay, right. Okay, moving on to the next one. Yeah, the wavelength relations. Atomic spectra, the last part of that particular chapter, like we know atomic spectra, when I told you energy related questions, transition of electron, that kind of questions repeatedly coming from this chapter. The other repeating concept is this atomic spectra. We are coming to that particular topic now, atomic spectra questions, right? Especially hydrogen spectra. We know Lyman series, Balmer series, Passion, Bracket and Fun series, right? We know the 5 series. We know the transitions. In each case we calculated maximum wavelength, minimum wavelength, right? And also which region they belongs to. All these questions, right? All these concepts we discussed already. We remember those, and now we'll try some questions from that part also. Electron in hydrogen atom jumps from third orbit to the second orbit. Third orbit to the second orbit. Orbits, okay, not excited states, orbits. N is equal to 3 to N is equal to 2. That is a transition. Fine. Wavelength of emitted waves, lambda is to be calculated. We know the relation wave number of emitted radiation for any atom. Wave number of emitted radiation 1 by lambda is equal to Z square R into 1 by Ni square minus 1 by Nf square. This was the equation, right? 1 by Ni square minus 1 by Nf square. And when we come to hydrogen atom, that Z reduces to 1. And what is that R stands for? R is the Rydberg constant, 1.097 into 10 raised to 7 meter inverse, right? That was the Rydberg constant. And in this question, we are talking about hydrogen atom, so forget Z square. Z is equal to 1. Okay, so then now we have to check the number of orbits, initial and final. Since we consider the emission spectrum of hydrogen, see, electrons are always excited from the lower energy level to higher energy level. In this question, it is given that third orbit, it is coming from third orbit to the second orbit. So the electron is transiting from third to second. N is equal to 3 to N is equal to 2. Which is your Ni and which is your Nf? That is the most confusing thing. Most of the time we commit mistake here. Remember, electrons are excited from their lower energy level. That electron actually belongs to the second orbit. It was excited to the third. Now it is coming back. Emission spectrum. Emission spectrum we consider only when the electrons de-excites from higher energy level to lower energy level. So that emission of radiation possible only in this case. So what is your initial energy level? Ni is 2. Nf is 3. Because electron is excited from its initial to final. Now they are coming back. Now that electron is coming back, right? De-excitation happens. So we can say Z is equal to 1 here. Hydrogen atom is given. Then 1 by lambda is going to be equal to R into Ni is equal to 2 and Nf is equal to 3. I hope, yes. Yeah, exactly. I am getting answers there. So Ni is equal to 2, Nf is equal to 3. Just substitute those values. 1 by Ni is 4 minus 1 by Nf square is going to be 3 square, that is 9. Correct? So we substituted the values. So we can simplify now. R into, we will take 36 as the LCM. So we have to multiply with 9 here. 9 minus 5. So we get 4 by 36 into R. And sorry, 9 by 4, so this is going to be 5, right? 5 by 36 into R. Fine. That is 1 by lambda. In the LHS we have 1 by lambda only. So what will be lambda? Lambda will be the reciprocal of this. Lambda is going to be 36 divided by 5R. 36 divided by 5R is the option A. Right. Okay, so transition, we just started questions from the transition. I think I can try 1 or 2 questions from this to give you one more concept, like 1 or 2 questions from the same concept, because time is already up. Yeah, okay, thank you. So let us try then. Next question, question number 16. Hydrogen atom, electron undergoes transition from third excited, yes, now we are careful, right? Third excited state to the first excited state and then to the ground state. The ratio of wavelength of the emitted radiations in the 2 cases will be, they are talking about 2 transitions. First transition from third excited. Can you tell me which will be third excited energy level? Third excited, it is not N is equal to 3. Exactly, N is equal to 4, right? N is equal to 4, third excited. Yes, third excited. And what is the other one? First excited state. First excited state. It is N is equal to 2. First excited is N is equal to 2. So this is the first transition. What is your Ni here? Tell me. What is your Ni? In this transition, it is coming from fourth to second. It actually went from second to fourth excited. Now it is coming back. So your Ni should be 2 and Nf should be 4. Correct? Yes. Then we can find out what is a ratio, wavelength there. 1 by lambda is equal to z square is equal to 1. We are talking about hydrogen atom. Yes. So R into Ni square. Ni square is going to be 1 by 4 minus 1 by 16. So 1 by lambda 1. I'll take the first one as lambda 1. Okay. R into 1 by lambda minus, 1 by 4 minus 1 by 16. You can take 16 as the LCM here. So we will get 4 minus 1 into R. And what is lambda 1? Lambda 1 is 16 divided by 3R. That is your equation number 1. Because you're asked to find ratio of wavelength in the two transitions. First transition we completed, third excited to first excited. Now what happens next? First excited was n is equal to 2. From n is equal to 2, it is coming back then to the ground state. Now it is coming back to the first energy level. So the second transition is from n is equal to 2. N is equal to 2. That is first excited coming back to ground state. N is equal to 1. Yes. In this case, Ni is equal to 1. Nf is equal to 2, right? Because it is excited from first to second. Now it is coming back from coming from second orbit to the first orbit back. So 1 by lambda 2 in this case is going to be R into 1 by Ni square is 1 minus 1 by 4. Yeah, exactly. So many answers I got already. So we get here 4 by 3 by 4. 3R by 4 is the ratio here. So lambda 2 is going to be just 4 by 3R. Equation number 2. Okay. Yes. Now take the ratio lambda 1 to lambda 2. You are asked to find out first excited, second excited to, third excited to second, that ratio to the next one. So lambda 1 by lambda 2 is to be calculated. So lambda 1 by lambda 2 we can take somewhere here. Lambda 1 by lambda 2, 16 by 3R divided by 4 by 3R. 4 by 3R, 3R gets cancelled. 16 by 4 is going to be just 4, right? So we get the ratio 4:1. Okay, so that is the way how we solve questions from the energy transition part, the lambda part. We have more questions from this, especially see in most of the cases I'll give you one more tip and we'll wind up. Okay, here whenever we have to go for this lambda, in these options we are asked to find the ratio of lambda so that R will be cancelled. When R is coming into the calculation, right, then it will be difficult to simplify. We'll get, suppose in this question we got 16 by 3R, right? 16 by 3R. That R is equal to 1.097 into 10 raised to 7. So we have to divide. That division is a little difficult. So I told you to remember that 1 by R value also. 1 by R if you know, then you can just multiply 16 by 3 into this value instead of dividing it, right? 1 by R is going to be 0.911 into 10 raised to minus 7, right, meters, reciprocal of that. So remember this, whenever we get 1 by R, just multiply with this value. Okay, just like we remembered 1 by E, right? In the condensation of atom, in the condensation of charges, electrostatics, we used this ratio frequently. Q is equal to Ne, 1 by E, that is 1 by 1.6, 0.625 into 10 raised to plus 19, that was the value. In the same way, I told you to remember epsilon 0 value also, 1 by epsilon 0, 1 by 8.854 into 10 raised to minus 12, it is going to be 0.11 into 10 raised to plus 12. Because in Gauss's theorem, we frequently use like flex phi is equal to Q by epsilon 0. So most of the time we have to divide with epsilon 0. Instead of dividing with 8.854, we can use this. Like that, in the wavelength calculation, whenever we get 1 by R, remember the value 0.911. Okay, into, instead of 10 raised to 7, it becomes 10 raised to minus 7. Okay, that is the only difference, 1 by R. 1 by 1.097 is going to be 0.11. Really, that helps you whenever there is a division comes with R. Exactly. Yeah. Yes, Dhruvi. But that's a dangerous connection actually. 911 is not something that we like to remember, but that you can use for the time being. 0.911. They will suggest that remember 911. Yeah, the tragic incident anyway. Yeah, hope we can wind up now. And one yes, yeah, but for the our intention is good, so it's okay, I understand. Okay, fine. Anyway, we'll wind up now. And one important information I have to share with you is like tomorrow, in view of Qatar National Day, there is no live at 9 o'clock. Sorry, Qatar National Sports Day, okay, not National Day, as you know. And there is no live class tomorrow, and it will continue from Wednesday onwards. Thank you all, and good night.
Brilliant Qatar, your trusted coaching partner for IIT, JE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.